Hello, welcome back to part 2 of lesson 6.4. This is the story problem section, and as a heads up, these problems can get quite tricky. However, having said that, you'll find that most of the problems are following a pretty good pattern. I call them two types, really. There's the working together problems, where two people are working together to do some work, and there are distance, rate, time questions. And there are all sorts of different ways of wording those distance, rate, time questions, but they all basically come down to the same thing. You're either asked to find the distance, the rate, or the time. So, we have a few problems here today of each type, and then tomorrow I'd like to just work on story problems for pretty well the whole class, and I'll give you some chances to do some extra ones as well to get prepared for the test. So this first type is a working together problem. Most likely will be on the final exam. So basically what I like to think about this one is, think of it as how much work each person is doing. What share of the work are they doing? Some people obviously have a slower rate. For example, in this one, two friends, Sheena can do it in 40 minutes, but Jeff, the same route take him 50. That means he must be going a little bit slower. So he's not going to, when they're working together, he's not going to be picking up as much of the work as Sheena would be. So we like to use a chart for this problem. So we think about Sheena on her own takes her 40 minutes to deliver the papers. Jeff on his own takes 50 minutes. We don't know yet how long it takes them to work together. In algebra, when we don't know something, we usually use a variable. So in this case, we don't know how long it's going to take them to do it together yet. So what we do then is we're going to put this into a fraction so that it basically makes one job 100% of the job. So Sheena's rate, in other words, is how much work she's doing in 1 minute. She's doing 1/40th of the work in 1 minute, whereas Jeff only does 1/50th of the work each minute. So if we follow that same pattern, working together is 1 over t, because we don't know the time together yet. All we know is that Sheena and Jeff together need to add up to the time together. So we don't know the number of work done yet that they're doing together. We call it t. So if I took this fraction and multiplied it by the t, that would be what proportion of the work Sheena's doing of it. So I took the 1/40th and multiplied it by the t, representing t minutes. Same thing for Jeff. Took his rate and multiplied it by the t. How much of the total job is he going to do? And then it has to equal 1, because it's one full job. Sheena's doing this portion, Jeff's doing this portion. And together they're doing 100% of the work. So once we have the chart made, this question becomes quite easy, and all of these ones are very, very similar, you'll find. The only small change is sometimes they will give you the t, the together time, and they will not give you one of the workers on their own. But it's just rearranging the formula. The same formula will always be used. So we're taking Sheena, amount of the work Sheena's doing, plus the amount of work that Jeff is doing, and that has to make 1. So again, just like in rational equations, we want to solve for t, so we want the denominator to disappear. We want to make an equivalent equation with no denominator. So that means I look at the common denominator here, and the common denominator is 200. So I'm going to multiply each part by 200, or in other words, just the missing piece. Okay? So 40 fits into 200 5 times. So I'm multiplying this piece by 5, this piece by 4, and this piece is going to get multiplied by the common denominator, which is 200. So altogether we've got 5t plus 4t, oops, not 49, 4t equals 200. 5t plus 4t makes 9t. 200. Solve for our t, or how long it takes them to do it together. So t is equal to, and that works out to be, I believe, 22 some minutes. 200 divided by 9, 22.2 minutes. So it takes them about 22 minutes. Okay, which makes sense. Remember, we're not thinking of it as an average. Many people assume I just take the average, but we can't just simply take these two and add it up and divide by 2 to say it's going to take them 45 minutes to do the job. Because remember, Sheena is going faster than Jeff. She can work faster than Jeff. So it's like them thinking about it as a weighted average, not a true average. Sheena's rate is faster than Jeff, so we can't just simply take an average of the work they're doing. All right? One for you to try on your own. Pause the video and you can try that one. And the answer to that problem, we can finish in 12/7 of an hour. More than an hour. Okay? And then you can try number 12 in the book that matches that type of question. Number 12 is very similar. Okay, now a distance, rate, time one. This is about a dog race that's held in the north, and it's held in Flin Flon. So we know the total distance of the race was 140 miles. Conditions were excellent on the way to Flin Flon, but bad weather caused the winner's speed to decrease on the return trip. The total time for the trip was 8.5 hours. What was the winning dog's time? Okay? Average speed, sorry, on the way. So a couple of things to do here. My personal favorite strategy on these type of problems is to pretend that it's me going on a trip and use fake numbers that are easy to do in my head. So if I visualize myself going to Summerside, on the way to Summerside, weather was great. Okay, so I went the 100 kilometers to Summerside, and let's say I was traveling 100 kilometers an hour, just to keep things nice and easy. So if I was going to Summerside, it was 100 kilometers was my distance, and I was going at a rate of 100 kilometers per hour, it took me 1 hour to get to Summerside. But on the way back, I encountered a storm. The same 100 kilometers was only, this time I had to reduce my speed. I must say, to make it easy, I reduced it by 50 kilometers an hour. But now instead of going 150 kilometers, it was taking me 50 kilometers was my speed, my rate. So this time it took me 2 hours to go. So you see how I can sort of use that information to figure out what I need to do. The other important thing is to remember the little formula. Distance equals rate times time. The other great thing that I like to do here with these type of problems is create a chart. So I'm going to have way there, let's say, way there, way back. And then I put in some information that I know of these pieces: distance, rate, time. Okay. So the total distance was 140 miles. That's there and back. Okay? So that means on the way there, my distance was 70. And on the way back, it was also 70. I covered the same distance both ways. Okay? Now, the next thing that I need to figure out is rate. Now, like my story problem. I picked a rate out of my head to show you what I would do. And I picked 100 kilometers an hour just to make it easy. But they don't tell us what it is in this table. All they tell us that on his way back, he was decreased by 6. We don't actually know his rate, what he started off with. When we don't know something in algebra, we use a variable. So on the way there, his speed was something. We don't know what it was. All we know is that on the way back, his speed, whatever it happened to be, let's say it was 10, it got decreased by 6. The 10 was decreased by 6. The x was decreased by 6. All right? Now, how am I going to represent time? Well, like in my example with the fake numbers, in order to find the time it took me to go to Summerside, I did 100 kilometers divided by my rate, kilometers per hour. So I'm going to do the same thing here. On my way there, my distance was 70, and my speed was x. Distance divided by time. Just like when you rearrange this formula, distance divided by rate would be equal to time. Same thing for this guy. 70 divided by his rate, we now know he's slower. Now what else do they tell us in the trip? We know the total time for the trip was 8.5 hours. So let's just put total. We can add that up. We knew it was 8.5 hours. 8.5 hours. So, in other words, way there and the way back equaled 8.5 hours. What should I do? What operation? When I say the word the way there and the way back was 8.5 hours. That little word and should be cluing you in. Plus, we're adding those two. So, the time it took them to go the first way, plus the time it took them to go home in the bad weather, added up to 8.5 hours. Now I'm going to use an improper fraction instead of that mixed fraction. So 8.5 hours is the same thing as saying 17 over 2. Right? 8.5? Because now I have a fraction. Alright, from here, it's fairly straightforward. It's just like the first part of 6.4, solving a rational equation. So we want to get rid of the denominator and then solve it. X is not allowed to be 0 or 6. So I look for a common denominator. The common denominator is a 2, an x, and an x minus 6. So this piece is missing a 2 and an x minus 6. And the 70. This piece is missing the x and the 2. And this part is missing the x and the x minus 6. No more denominator. All right, I'm going to do this first. 2 times 70 makes 140, and then multiply it by the x minus 6. Same thing here, 70 times 2 is 140 times the x. And over here, I will do 17x first. I'll just do it in 2 steps so people can see what I'm doing. And then use the distributive property. So I'm going to use the distributive property here. 140x minus, and that's going to give me 840. Plus 140x is 17x squared minus, and that's going to give me 60 and 42, 102x. Okay. Now it's time to collect our like terms. So we've got here 140x plus 140x. That's going to be 280x minus 840. equals 17x squared minus 102x. Now I'm going to bring this to the other side and bring this over here as well. So I'm left with 0 over here, 17x squared minus 382x plus 840. All right. So at this point, it's probably going to be most conducive to use the quadratic formula, okay? Because we don't want to try to factor that, so we're going to use the quadratic formula here. And when you put it into the quadratic formula, you're going to get two answers. X equals 20, or x equals 42 over 17. Okay, so at this point we should check to see that they don't meet any non-permissibles, which they don't. But we also want to make sure that they also make sense. When you check them, they both might work, left side, right side, but let's see if it actually makes sense. So this solution right here, 42 over 17, this is not, that's the same thing as about 3 point something, right? Or even 2 point something. So if we had, what is that actually? 42 divided by 17, 2.5, about 2.5, approximately 2.5. So just go back for a second and look at our original equation. Remember, this represented, we just finished solving for x, and that was the speed that the dogs were going, 2.5 miles per hour in good weather. Well, if we reduce 6 from 2.5, that's not possible. The dogs cannot be going negative speed. So this is not an acceptable answer right here. This one is not acceptable. Extraneous root. So it didn't meet the conditions of the story problem. This one is acceptable. It works. The dogs were going 20 miles per hour. Is that what they were asking us for? Let's go back up. What was the winning dog team's average speed on the way to Flin Flon? The winning team's speed was 20 miles per hour. Okay? Pause the video here to try this problem on your own. Now, I'm actually going to do this one out as well because this one's slightly different than the last one. Similar to my question I talked about Summerside, because a train has a scheduled run of 160 kilometers between two cities in Saskatchewan. If the average speed is decreased by 16, the run will take half an hour longer. So think about this, like my Summerside trip. In good weather, it took me an hour. In the bad weather, when I had to reduce my speed by 50, it took me 2 hours, so it was 1 hour longer. So if I thought about that in context, how would I get the 1 hour longer? I would take my slower time, subtract my faster time, would give me 1 hour. So, in other words, how would I write that in words, first of all? So, time in good, it doesn't tell us in this problem that it has to do. Time in good weather, doesn't say if that's the reason, but I'll go with that. Subtract, the other way around, time in bad weather, right? That's the slower one. Time in bad weather. Subtract the time in good. is the half an hour longer. Okay? Or you could simply put, and you can do it lots of different ways of how you want to set it up, but you could also add this. The time that you take in good weather plus the half would give you the time in bad weather, plus the half an hour. All right, so it's not like the last one we divided up the 140 because that was the race. It was 140 total distance, but this is just two separate runs. One day I went on the train and it took me 2 hours. The next day I went on the train, it took me 3 hours. Or let's say 2.5, so it makes that. So it was a half an hour longer, but it was still the same scheduled run. So again, we want to create a little chart here. Distance, rate, time. Okay? Let's call it run number 1 and run number 2. Scheduled runs. So the first run, he was scheduled of 160. We don't know his rate. It doesn't tell us the rate. So again, we're using X. All we know is that on run number 2, his average speed decreased by 16. The word decrease means subtract. So just like in our Flin-Flon problem, to get time, I'm going to do 160 divided by the rate, distance divided by rate. So 160 divided by X. And this one would be 160 divided by X minus 16. All right? Now, I'm going to go back up to my words here that I sorted it out in my head of what I should be doing this time. Because it doesn't give me a total time this time. It just told me that it took half an hour longer. So I'm going to take the time in bad weather, or run number 2. That's the time from run number 2. Subtract the time in good weather, and that would be a half hour longer. Fake numbers again. 2.5 hours, run number 2. 2 hours, run number 1, when it was good weather. Subtract the 2 will give me a half an hour longer. All right, then we go through the math of solving that. So again, just like the Flin-Flon problem, we would find the common denominator. This piece is missing a 2 and an X. And this piece is missing the 2 and the X minus 16. This one is missing the X and the X minus 16. All right, so when we figure this out, 2 times 160 is going to give us 320X. And again, that's going to be 320X. I'm going to use a subtraction sign here. This is going to be 320 times X, and then you would also do 320 times negative 16, which would be negative 5,120 is equal to X squared minus 16X. Let's simplify this a little bit. 320X minus 320X, those will cancel each other out. But negative negative would make positive 5,120. So I can just move this to the other side, and that would be 0 is equal to X squared minus 16X minus 5,120. All right, at this point we would use the quadratic formula, or when I think of the quadratic formula would be more conducive to this question. And you get 2 answers. X is equal to 80 and X is equal to negative 64. Well, obviously this one's out because you can't have a negative speed. This one's out, so this is to be the right answer. Let's see if it makes sense. Let's just see. If his speed was 80, we would be doing 160 divided by 80 subtract 16, so 64. 2.5 hours on run 2, subtract 2 hours, because 160 divided by 80 is 2, gives me a half an hour. So the train was traveling about, what is the average speed of the train? Average speed of the train is 80 kilometers per hour. And that's it. You should try those problems now for homework. Please do them all because they're very common exam, final exam questions.